Hello, everyone. Come on in. How's my audio and video looking so far?
Looking good on my end so far.
Let's see if it sticks with that. It's weird. It's got not giving me the option to show any chats. Oh, there it is. Hello, I'm so smart. Well, I am so smart. SMRT, SMRT. All right. While we're waiting for other people to come in, looks like we're up to 9 so far. Does anybody have any questions? I mean, last met, I think we finished off chapter 11 with some more examples. And that's really, I'm not going as deep in chapter 11 as maybe some instructors do. I think it's pretty self-explanatory. Having studied conservation of regular momentum and conservation of energy, I think conservation of angular momentum is just a new formula that you use to make conservation laws with. So that should be pretty straightforward. The ramifications, of course, are quite important, but I think y'all probably already know those from everyday life, whether it be swinging in tire swings or spinning in tire swings more specifically, or, spinning ice skaters and stuff like that. Then seeing how that relates to how the planets move, I think we've got a pretty good understanding of conservation of angular momentum. I will tell you something neat about it, though. In conservation of angular momentum, it's the reason that if you ever take a motorcycle driving course, which I took just for the fun of it, because I bought a motorcycle when I knew they'd actually give you cheaper insurance rates and stuff like that. So I took the course, and it was kind of weird because they told me something. I've been riding bikes, like I used to ride freestyle, on half pipes and quarter pipes, and actually I was mostly more into street riding, but anyways, I did do half pipes a lot, not that much quarter pipes. But I rode motorcycles as well, just not nearly as much. But when I got there and they told me about how to turn, I was like, oh, this is some weird crap right here. So I'm going to explain that a little bit to you and let you try to play with the conservation of angular momentum and see how that actually works. But basically, when you take a motorcycle driving course, they'll tell you when you're driving at speed like this. Let's say I got my handlebars like this. They're actually obviously a lot wider than that, but this gives you the idea of what you're doing. So normally I think if I want to turn right, I'm going to turn my handlebars right and I'll go right? And in actuality, I never even think about turning my handlebars, especially at speed. I mean, if you're going really slow, yeah, you turn your handlebars on a bike or a motorcycle or whatever, and that works fine. But over a certain speed, you don't even think about turning your steering wheel or your handlebars. You just sort of lean and it happens, right? That's sort of the way I've always done it. But I get to my motorcycle safety course, motorcycle safety and driving course, and they said, all right, when you go to turn lanes, you want to push right to go right. I'm like, what did he just say? He said, no, seriously, I mean, go out and try it now. So literally what he's saying is if I want to turn this way, I push forward with my handlebars that way. And he's right. I tried it that afternoon. So literally it says, hey, if you want to go right, which is this side for me, you push right. And what literally happens is via conservation of angular momentum, there's no net torque on the system. So what you just did is made an internal torque on the system where you took the angular momentum that was this way because the tires are rolling this way. Therefore, if you curl your fingers in it, your right thumb points that way. So the angular momentum was that way. And you just applied an angular momentum this way. It tries to respond by doing basically sort of the opposite. In other words, it tries to restore what it had, which was this way. So the way you do so is you actually cause the angular momentum to tip over. In other words, it causes the motorcycle to tip, and then that's actually what causes you to turn. So it's kind of a neat little exercise, but that is basically an application of conservation of angular momentum. So if y'all happen to ride motorcycles, I love it. I think it's awesome. It's really a lot of fun. I'd tell you to stop doing it really soon. That's why I stopped. I had multiple friends have been killed motorcycles, and almost never their fault. It's really a horrible situation. So that's why I stopped doing it. But just be careful. But anyways, that is a kind of neat little thing that you can learn just from conservation of angular momentum. So now I've got 16 people in here. So I'm going to go ahead and get started. We're going from chapter 11 now. We're skipping 12 and 13. 12's on statics, which obviously if you're taking an engineering program of any sort, I think all engineering, even chemical engineering, requires you to take statics. You'll get a much more thorough treatment there, and it's actually fun stuff. I love it. There's some really good books in Dover print that are made for statics, dynamics, and for strength of materials. So I definitely recommend them. Like Herzog is the author, Herzog. And I taught that all to myself before I went into structural engineering, just because it was interesting. Then chapter 13 is fluid mechanics, which if you're a mechanical engineer and maybe certain civil engineers and aeronautical engineers and maybe even chemical engineers, they're going to take that as well. So we skip that. But you can actually read those chapters, do those homework problems, and get extra credit for them. So they're still available as homework problems, but they're just extra credit, and they have to be due by December 15th at midnight or 11:59 p.m. So that being said, we jump into chapter 14, which is basically just called oscillations. And that's what I'm going to teach you about now. And I'm going to, preface it by telling you, us physicists are not so nerdy and devoid of excitement that we pride ourselves on studying springs because they're the most interesting thing in the world. It's nothing like that at all. In fact, springs are, kind of boring. But the cool thing is that springs happen to create Newton's second law, especially if you include air resistance, that is really, really super interesting. And the reason why it's super interesting is because all things in matter, or many, if not all things in, that matter in the universe, have some tie to oscillatory motion or simple harmonic motion, or basically the differential equation that tells you how a mass on a spring behaves is exactly the same differential equation that you get for many walks of life. So for instance, when you get into 242, we'll do RC circuits, which is resistors and capacitors in a circuit. And you can charge a resistor up, and then charge a capacitor up by running a battery, running a current through a resistor, and then charging up a capacitor, and then you could have that capacitor say across a diode or something like that, and that would make an oscillatory circuit. In fact, the differential equation is very much like the differential equation that you get for mass on a spring. Same thing with the LRC circuit. So you take an inductor, a resistor, and a capacitor, and lo and behold, it's the same equation. So those are two. If you just talk about an object on a pendulum, which is could be a pendulum, could be a clock pendulum, could be a person or kid swinging on a swing. It could be a mass hanging from a large crane that you're trying to lift to build a building. All those things are all oscillatory motion. In fact, if you actually decide to crank that mass up with the crane, that ends up becoming a more fancy differential equation that involves vessel functions, which is a whole different branch of differential equations. But still, it all sort of starts with that simple harmonic oscillator. And then here, this is the biggest argument for all of it. It turns out that whenever you take something that has a stable equilibrium point, so for instance, if you make a plot of potential energy versus distance, the potential energy might go like this, and then it'll reach some minimum. That's the stable equilibrium point, is that minimum. And it's stable because if you give it a little perturbation where it goes away from stability, that curve tells it it's going to go back to that stable point, maybe swing past it and then come back, and so on and so forth. Also, if you go the other way, then that curve is going to tell it to come back. So no matter which side you're on, it's always going to tell it to come back to that lowest point. That is the actual stable equilibrium point. So when you have a potential energy curve that has a minima like that, that's a stable point of equilibrium. It's called stable equilibrium. Now, here's the neat thing about that. Can anybody tell me what the derivative of that potential energy function is right there at that minimum? What's the derivative of the potential energy function if it goes like this and then reaches that minimum and then goes back up? What is the first derivative of that potential energy function right at the bottom of that well? Yes. Randall said 0, and that's exactly right. Remember, the derivative for starters is a slope, so you can obviously see if something's at the bottom, its slope is horizontal, so it's literally 0 slope, or its angle is horizontal, so it's 0 slope. The other thing is that's sort of the definition of a minima. A minima is the first derivative equals 0, and of course you got to remember the second derivative has to be positive, and then the maximum, of course, is the first derivative of 0, and the second derivative is negative. And then if the second derivative is actually 0, it's a point of inflection, which would go like this, like that. Okay. So that's an important point. Also, and remember that when we did, for instance, potential energy, you could take the ground level to be potential energy equals 0, or you could take the lowest level, say on a roller coaster. The lowest level that the car reaches on the roller coaster is possibly quite a bit higher or even lower than the ground level. But you can use either of those as the 0 of potential energy. So with that, I think you can understand that you can add any basic quantity to a potential energy function, and you still get the same potential energy function, because all that really matters when you're dealing with potential energy is the change in potential energy, not the absolute potential energy. So you can count the center of the earth as the 0 potential energy. You can count the sea level as the 0 potential energy. You can count Mile High Stadium in Colorado as the 0 potential energy. Doesn't matter. That's just adding a constant to the potential. Now that you have that background, let me remind you something from calculus. So there's something called a Taylor series expansion, where you can basically, at least if it meets certain criteria, and if it's near a certain point, blah, 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 you can actually write a function as a representative of, or as being represented by a series of derivatives of the function. Okay, that's called the Taylor series when you expand it about a point A. So you consider close to the point x equal A, then the value of the function f of x near that point is given by this Taylor series. There's also another one called the Maclaurin series, where you're close to the point x equals 0. And then as long as you're close to 0, that sum gets you closer and closer to what the actual function is, slightly different from x equals 0. Those are Taylor Maclaurin series. I've got them written out here. So now I'm going to do that Taylor series, and I'm going to recommend to you, you do this. This is something that's going to appear over and over in physics and engineering, in chemistry. Even sometimes you can see it come up in biology, though they normally don't teach that portion of it, but it's still something that biologists have found useful. But the basic thing is, I'm going to now show you why the harmonic oscillator, i.e. a mass on a spring, i.e. pendulum oscillating at a small angle, are all parts of everyday life. So here it is. Let's turn on my document cam. So this is the Taylor series expansion. It says f of x, and again, it's certain mathematical conditions have to be true for this to work, but it turns out that just about every function you could possibly run into for a physical problem is going to automatically meet those criteria. Okay, so that's why we hardly ever worry about such things in physics when we apply Taylor series expansions and Maclaurin series expansion. But I will tell you that certain people have made their careers off not assuming such things, and discovering that people had been assuming such things about certain functions, and literally made their name as a great physicist in that realm. So here's a Taylor series expansion. It basically says that it's a summation from I equals 0. I wrote 1 on an earlier version of this for class, and that was a boo-boo, but I equals 0 to infinity of 1 over I factorial. Remember, factorial means, like, if it's 5 factorial, you take 5 and multiply it by 4, and then by 3, and then by 2, and then by 1, and that's what factorial means. And then the ith derivative of the function evaluated at a times parentheses x minus a to the ith power. That's the Taylor series. The Maclaurin is, and I think that's the spelling. I always forget whether it's MC or MAC, but I think it's that. The Maclaurin is a special case of the Taylor series where a happens to be 0, and that's the one I'm going to use. It's f of x is equal to summation from I equals 0 to infinity of 1 over I factorial, the ith derivative of f evaluated at 0, and then x to the I. I recommend you do this with f of x equals sine x. I recommend you do this with f of x equal cosine x. And I recommend you do this with f of x equal e to the x. And really, if you can have time, I would recommend you do it with f of x equals 1 plus or minus x raised to the n power. All of those are really wonderful. I would say carry them out. You'll see a pattern with these first three. You're going to see a pattern actually with all four of them. You'll see a pattern where you can basically, once you write 5 terms or maybe 10 terms, you'll know the pattern from there on out. So you really only have to take 5 or 10 derivatives. But not only that, when you do that, you can see if you go and make the replacement of f of x, if you make that into f of theta equals e to the I theta, in other words, we actually replace x with I times theta, where I is the square root of -1, not that I, that's a different I, right? When you do that, you'll figure out that in fact, this is cosine theta plus I sine theta, which is Euler's formula. It's a famous thing that comes in handy too, especially in solving differential equations, which we're getting ready to go into. That's Euler's formula. But by that Taylor series expansion with sine x and cosine x, you'll see basically a buttload of zeros, and actually no zeros. But when you put in I theta in place of x after you've done those expansions, you'll see certain terms come up with an I in front of it. You group all those together, and lo and behold, what'll be left is the sine theta expansion. And then a bunch of terms have no I's in front of it, and what will be left is the cosine theta function. So that's kind of neat. So with that in mind, now let me go to the Taylor series expansion, which is why, or excuse me, Maclaurin series expansion, which is why I wanted you to understand that the harmonic oscillator is representative of everything in nature in some sense. Okay, so we talked about potential energy. Remember, the potential energy for a mass on a spring, we've done this derivation before, it's just 1/2 k times x squared. So 1/2 of a constant times x to the second power. We also learned that u prime is equal to u plus a constant is perfectly valid. In other words, this is okay. You're not going to have any problems whatsoever, right? And we've also learned that the potential energy du dx, its derivative at a minimum is equal to 0, right? So now let's look at this Maclaurin series. Let's assume we're looking at a function like this, say. Here's our potential energy function. And in fact, it goes like this. Or anything, long as it just has a minimum of x equals 0. That's the key point. Then what you see is when you do the Taylor series expansion, I've got the function evaluated at 0, right? And it doesn't have to be like that. I actually drew it like that, but it could be just like this as well. The main thing is the minimum is that x equals 0. But obviously, if it's this, then this f of 0 is going to be a negative quantity. If it's this f of 0 is going to be 0. But the main thing is it's going to be a constant just like that constant. Not only that, since you're at x equals 0, the derivative is equal to 0. So this one's going to be 0. So this one's a constant. This one's 0. And then the first thing you got left is 1 over 2 factorial. Well, 2 factorial is just 2 times 1, so that's just 1/2. And this is f, the second derivative evaluated at 0. That's a constant. And this is x squared. That's the same as this. So yeah, everything near a minimum is going to have a potential energy like 1/2 kx squared. That's why even in quantum mechanics, like the third major problem you solve, at least in a graduate level quantum mechanics course, if not a really good undergraduate level, is something called the harmonic oscillator, where they literally imagine a spring holding, 1 electron to the nucleus of an atom, or holding 1 atom to the molecule. And you think that's the stupidest thing in the world. Obviously, there's no springs at that level, but in reality, there is, because look, everything behaves like a spring, at least to the first 3 terms. And these would be corrections, because obviously, if you get, really close to x equals 0, this number is going to be really, really small. And if you cube it, like if it's 0.001, if you square that, then that was 1/1000th. That's going to be 1/1,000,000th. But if you cube that, then it's going to be 1/1,000,000,000th. If you quadruple that, it's going to be 1 times 10 to the -12th. So you can see these other terms are going to be irrelevant. And this is the leading thing. So that's why we study springs so much in physics. It's not because we like springs. It's not because we obsess about springs. It's because springs are, in some sense, in differential equations everywhere. All right. So now that we have that underway, does anybody have any questions about that? It's a highbrow thinking sort of thing, meaning it's kind of a deep concept, but it's the reason we do this. And I want all my calculus-based physics students to leave knowing why we study harmonic oscillator so much, or why we study masses and springs so much. So does anyone have any questions on that? Okay, so the next thing I want to do is I want to apply Newton's second law. So now we're going to talk about oscillations. And I'm going to apply Newton's second law. And we've now, since we covered momentum and angular momentum, we've learned something about Newton's second law. We had been treating Newton's second law as F equals ma. Well, what we learned was Newton originally said, and therefore what is more generally correct is the summation of the forces is equal to dp dt. That's the more correct statement. So MA is not necessarily the correct answer. That just happens to be okay when the mass doesn't change significantly. If you want the mass to change while the forces are acting, then you're going to have to use this. And therefore you end up taking the derivative of M with respect to T times V plus the derivative, or plus mass times the derivative of velocity with respect to time. So there's an extra term that comes in. So with that in mind, we're going to use basically the old form, because we know it's d by dt of mv, but that's equal to m dv dt. And if m is a constant, we're good with that. But it's also v times dm dt. And in this case, we're going to say that's equal to 0. So that's what's going on here. And not only that, I'm going to imagine my problem as this. So here is the ceiling. Okay. And I have a spring, a relaxed spring hanging like so. Okay. Now, what I'm going to do is I'm going to say, this is the relaxed position of the spring. Now I'm going to take and hang a mass on the spring. And as long as I don't exceed its elastic limit, there's a law called Hooke's law that tells me how this X is related to the force hanging on it. And in fact, Hooke's law is that, so here it is. Y'all have learned it already, but I'm just restating it here. Hooke's law says that the force is equal to negative kx. And I think you see that, right? The force that's actually applied to the mass m is acting that way. And the stretch is in fact this way. That's why the negative is there. So if you ever need just magnitudes and you don't have to worry about direction, then you're not going to use that negative. But if you actually need to take into account direction, then you need to use that negative. Okay. So with this one, what we can see is really the force has to be applied such that it counteracts this force. And this force is, of course, mg. So Newton's second law in this case becomes mg, right, is equal to negative kx, basically. Or now we can use Newton's, I meant to say this is the equilibrium condition sort of, but let me say now with Newton's second law, that means negative kx is equal to m times dv dt. Okay, which I can also write as m times d2x over dt squared is equal to negative kx. And finally, I'm going to write it a little more wisely. I'm going to put everything on one side of the equation, but I'm also going to divide through by m. So I'm going to divide through by m. Whatever I do to one side, I must do to the other. And I'm going to put everything on one side. So I get d2x over dt squared plus k over m times x is equal to 0. That is the simplest version of the harmonic oscillator differential equation. Okay, it's called a ordinary second order because it's the second derivative linear, and that means it doesn't have any x times dx dt or dx dt times dx dt or x squared and that kind of stuff in it. So it's linear and it's homogeneous. Differential equation, which I'll write diff eq. That's the normal abbreviation people use for the course differential equation. So that's the type of differential equation it is. And basically what it has is constant coefficients with orders of derivatives, which in this case happens to be second. You could have a third order derivative, fourth order derivative, so on and so forth. And the technique for this is you look at this and realize, wait a second, if I can ever find a function whose derivative just repeats the function, in other words, I take the derivative of something and I get something times the original function, then that's awesome. That would be perfect. That's exactly the kind of solution I need. Well, we know sort of that. We know one, for instance, we know that, for instance, if you take the derivative of e to the x, you get e to the x. You take the derivative of e to the x for the second time, you still get e to the x, and third time you get e to the x. So that would put an e to the x in every term. Well, that's really wonderful because then you have a what we call a characteristic equation that's just you know, a quadratic or something like that. But we also know there's another one, and that's the trig functions, but they're kind of funny because the trig functions don't necessarily always repeat themselves, because when we take the derivative of sine, we don't get sine back, we get cosine. And when we take the derivative of cosine, we don't get cosine back, we get sine, right? Or negative sine. So that is still an idea that we need to consider. And in this case, we're really going to consider it because I'm really only doing a second derivative and no derivative. So that actually accounts for the problem of if I used a sine, it's going to become a cosine and then become a sine again after the second derivative. So what we do is we sort of guess at a solution, and you can actually do that with all differential equations. It's just the likelihood of you guessing the right function is nil, right? So we call this, or at least in German, they call it an Onsites. So an Onsite solution. So it's just a guess, basically. So I'm going to say Onsites. Let's assume, because I suspect this thing's going to oscillate back and forth in time. So I expect it's going to have some max amplitude. It's going to have some period and some frequency. And let's assume x of t is equal to some constant a times cosine omega t plus phi. Okay. Now, I did something very smart there that most people don't necessarily think of, but here's the reasoning. Can anybody tell me, how do you undo a derivative? What mathematical operation undoes a derivative?
You take the antiderivative.
I couldn't make out what that was. What did you say?
The antiderivative.
Yeah, the antiderivative. And anybody remember another name for the antiderivative?
Integral.
Exactly. So what mathematical operation undoes a derivative? And you guys wisely said the antiderivative, which is actually also the integral. So integration. Now I'm going to ask you another question. What is the integral of x squared dx? It's not a trick question. It's supposed to be as easy as you think it is. Yes, Makita and a couple other people typed it in. Michaela, Makita both typed it in.
And the answer is the integral of x squared dx. They left off a little point, and that's sad because that's the one part that I needed more than anything. I bet now that they heard that, though, I bet you they know what part they left off. The answer is 1/3 x cubed. There you go. Plus a constant, which I'll call C1. Okay, so plus a constant. See, when you have a differential equation, what you have is an equation relating derivatives to maybe other derivatives and other variables and stuff like that. So in some sense, solving a differential equation really is integrating, right? In this case, I actually have a double derivative, so I really need to integrate twice. So now I'm going to ask you, what is the integral of 1/3 x cubed plus C1 dx? And y'all are going to say, is equal to, let me do the hard part for you. The arithmetic is 1/12. So then I'm going to have x to the 4th, right? But what's the integral of C1? Anyone? And is that all? Okay, I went ahead and answered the question about what the integral of C1 is, but am I done? Is that the whole answer for this integral? I'm not, am I? I need another constant. So I'm gonna call that C2. Now you see why I called the first one C1. And so that's sort of the point, okay? Each time you have a derivative, to undo it, you got to take an integral. And each time you undo an integral, or excuse me, undo a derivative by doing an integral, you introduce a constant. That constant is normally handled by range of integration, right? But it's also can be handled by initial conditions, or what we call sometimes boundary conditions if we're dealing with space as opposed to time. So if I have a second order differential equation here, you should expect that I'm going to need two initial boundary conditions, or two initial conditions. And that could be like x at t equals 0 is 14 meters, or x prime, which would be the velocity at t equal 2.4 seconds, is equal to 3.8 meters per second. Two of those equations is what's going to be needed to actually solve this. So you got to have, not only in addition to some way of guessing a solution, then you've got to have some initial data to make sure you can understand stuff. Since this was a second order differential equation, I put in two additional constants, a and phi, to make sure that I had enough range to make it fit whatever initial conditions I had. I actually put in 3, but as you'll see, this third one's going to be figured out by the nature of the equation itself. So now I want to go back to this. My Onsites was, let's assume x of t is equal to cosine omega t plus phi. This is important for you guys, by the way. This is going to be your solution for this particular harmonic oscillator every freaking time, okay? And then you can take your initial conditions and use it to figure out what a and phi is. So you don't have to go through this derivation of deriving what the solution to a differential equation is. We gave it to you, but now I'm going to show you how it works. So x of t equals a cosine omega t plus phi makes us realize that dx over dt is going to be, the derivative of cosine, of course, is a negative sign. So I have to put a negative in front of it. Of course, the a is still going to be there. And now the cosine has become sine, but that's just the derivative of cosine with respect to the argument. What's the derivative, using the chain rule? What's the derivative of the argument with respect to time? Anyone? These interactive classes are a lot more interactive when you guys are willing to talk. The derivative of omega t plus phi is just omega, so I got to put omega out in front. Okay. Now, the second derivative with respect to time squared. Notice that's in the equation. The first one wasn't, but I couldn't get the second one without getting the first one, so I had to do it anyways. Now the derivative of sine is just cosine, but the negative is already there, so it's going to have to stay there. So I get negative omega a cosine omega t plus phi, and life is looking pretty sweet, right? But here's the deal. I now got to take the derivative of omega t plus phi with respect to t, so that omega is going to become omega squared. And you probably remember, of course, why I labeled this A. Anybody know why I called that A? Do y'all remember that from pre-calculus? Remember, your cosine graph in principle looks like this, and it goes from +1 to -1 back to +1 in a distance of 2 pi, where whatever your function is, in this case, it's a function of x. And in this case, it would just be 1, but by putting a in front of it, what does that become? It becomes a, okay? So this is your amplitude. Now, the other thing is, what if you started looking at it not when the spring was fully stretched? Well, then it would look something crazy like this. Maybe it'd be, maybe it'd go up, do that, come down this way, do that, and then come back here, and then come back there or something, right? If that's the case, then the period is actually ends here. But what you see is we'd have to shift it some bit. Well, that's what this is for. And that's called the phase angle or phase shift. So you can see by adding those two constants, what it's done, it's allowed me to affix an amplitude to it, and it's allowed me to fix a phase to it so we can tell what it's going to look like, because we're not always going to start looking just when the when the mass on the spring is fully elongated. Okay, so now that we have that information out of the way, we can now go ahead and plug this stuff into the differential equation. So we had d2x over dt squared. Well, that's negative omega squared a sine, or excuse me, cosine omega t plus phi, plus we have k over m, k over m times x. So that's going to be k over m times x, which is just a cosine omega t plus phi, and all that's equal to 0. Well, the problem is this is Newton's second law. I say the problem, it's actually the solution. So it must be true at all time. Okay, because of that, we can say negative omega squared plus k over m, factor that out, times a cosine omega t plus phi. This part can't be 0 at all time unless I force phi and omega to be 0. And even then it's going to be 1, right? So it don't even work, right? I could force, omega t plus phi to be equal to pi over 2. And then, yeah, that would be it. But this has got to be true all time. And there's no way you can make a omega t plus phi equal to pi over 2 for all time. So what that forces is this has to be 0 at all times. So you get omega has to be the square root of k over m. And lo and behold, that omega is exactly the omega we studied in rotational motion. That omega is equal to 2 pi times the frequency. And of course, with that comes the added information that the frequency is 1 over the period, so that the period is 1 over the frequency, which would be the frequency is omega over 2 pi. So this would be 2 pi over omega. And 2 pi over omega is just 2 pi times the square root of m over k, which you hopefully recall from other material as well as from the lab that we do this week. So I'm going to go ahead and circle these. These are all critical things. So just like the x equals a cosine omega t plus phi, you're just going to use these things. You don't have to go through and derive it every time. You're just going to use these facts and get your answer every time. So that's it. That's the solution of the differential equation. And in fact, it also works when we add a term for the air resistance, or let's say well, let's just say resistance in general, because it could be an object sitting in liquid, in which case it's sort of it's still a resistance, but it's a liquid resistance. Okay. So we've got that. Now let's look at an actual example and see if we can make any sense of it. The first example is going to be the lowest hanging of the fruit, and that's going to be the typical problem that we always give you when we first introduce Hooke's law. So this will be example 1. It says 2 large men, let's say 2 large people, sit in a 1200, let's do 1500. I like that number better. In a 1500 kilogram car with spring suspension. Now, this isn't necessary. I mean, even shock absorbers have a sort of spring constant type behavior, so it would work even if they were just shock absorbers. But almost all of them have a spring plus a shock absorber scenario, but you can definitely assign a K to it no matter what. So spring suspension. If the men, or if the people, have a total mass of 500.0 kilograms, and I should actually probably say this is 0.0 as well, and the car drops by let's say 4.0, no, let's do 3.00. What is K? That'll be part A. And part B, what drop would occur if 2 similar people sat in it with M total equals 300.0 kilograms. So that's part B. Okay. Remember what I told you about Hooke's law. Hooke's law has the negative in it when you're talking about the magnitudes and direction, but you can drop the negative when you just talk about the magnitudes. So we can say, here's our solution. We know that F is equal to Kx, and in this case, F is mg. So we can say K must be equal to mg over x, or for part B, we can also conclude that x must be mg over K. So our solution for part A is just going to be K is equal to 500.0 kilograms times 9.80 meters per second over 0.0300 meters. Notice that is actually newtons per meter. We don't want it in newtons per centimeter. That's why I converted that to meters. So we get K is actually equal to, I think the number comes out to be 163. Let's double check. 500 times 9.8 divided by 0.03 is, yes, 163 newtons per meter. So there's A, right? Easy enough. Now B is just as easy. We're just using a different mass. So B, we get X is equal to 300 kilograms times 9.80 meters per second over this case, we're going to divide by 163.33. There's extra sig figs there that I put and underlined, and that's newtons per meter. So you can see kilogram meter per second squared on top's a newton. I'm dividing it by newton per meter. So this will come out in meters. So now I'm going to do 300 times 9.8. And then I'll divide that by 163.333. And I get about 18. Whoa, that's not right. Yeah, that's right. 300 times 9.8. Oh, duh. Here's the problem. I said 163. Did anybody verify that? It's actually 163 times 10 to the third newtons per meter. So that's a lot different, right? 163 times 10 to the third. So I need to put that in there. So times 10 to the third. And then you, of course, get 1.8 centimeters. I've actually already done the conversion, but basically it's 0.0180. So to proper sig figs, I should put a 0 there. So 1.80 centimeters is the answer. I think that's pretty straightforward, right? That's a fairly straightforward, easy problem you've probably done 1,000 times before, maybe even in high school physics if you were fortunate enough to take that. So any questions on that? All right, so now I'm going to do another problem, and this time I'm going to actually make use of the equation and of the stuff that we discovered about the differential equation. So what I'm going to do is I'm going to say this is example 2. And what I'm going to imagine is a first hang a mass from a spring. And then, of course, the equilibrium position of the spring is just this. But once I hang the mass, then it's going to do this thing again. So that the X is X1 equals, let's say this is going to be 7.00 centimeters. And let's say the mass that was hanging on it was 1 kilogram. Okay, now I'm going to take that same mass and that same spring, and I'm going to lie them on a nearly horizontal frictionless surface. It's going to be a horizontal, but it's going to be nearly frictionless surface. Okay. And it's still that same mass. And I am, in fact, going to pull it out to, let's say, from its equilibrium position, I'm going to pull it out to 9.00 centimeters and let it go. So pull it out to 9.00 centimeters from equilibrium and release. Oh, I left off an E in there. I'll put it right there. Okay, and release. What is K and omega and T? And then I'll call that part A. Put a period there. Part B. What is A phi x of t? I'm going to say V of t and A of t. Okay, so that's our problem. Our solution. For part A, I'm just going to say, hey, K is equal to 1.00 kilograms over 9.80 meters per second over 0.0700 meters. That gives me 9.8 divided by 0.07. That gives me 140 and 40.0 extra sig fig newtons per meter. Omega is equal to square root of 140.0 newtons per meter, square root of K over M, and M is 1.00 kilogram. So omega is going to be equal to, take 140 divided by 1, take the square root of that, which is just the square root of 140, and that's 11.832. And that's radians per second. So we've got another answer here. Now, I didn't ask for the frequency, but in order to get the period, you normally calculate the frequency and then do 1 over the frequency for the period. So I might as well do that as well. Frequency, remember, omega is equal to 2 pi f. So f is equal to omega over 2 pi. In other words, you got to take the radians out and convert it to degrees. So that's going to give me 11.832 divided by 2 times pi. If you do 2 times pi, you need to put it in parentheses to keep from making a mistake. And that gives me 1.8831. And that's hertz, our cycles per second. Okay. And that means the period is 1 over the frequency, and that's seconds per cycle. So it's really just, you can just call it seconds. So I'll say 1 divided by that answer, and I get 0.531 03 seconds. So there's our period. So we basically got part A done. Now we're actually a little bit over time. We're right at 11:52. I'll just tell you now, these initial conditions are actually given here. When I say I pulled it out to 9 centimeters, what I just basically gave you was x of 0 is equal to 0.0900 meters. And what I also gave you was that the velocity was 0, because releasing it just means I dropped it or I let it go. I didn't give it a push. So x prime of 0 or x dot of 0, whatever you want to call it, which is also v of 0, that's equal to 0.00 meters per second. Those two initial conditions are enough to allow us to evaluate all this. So everybody's free to go. I'm going to finish this out for anybody that can stay, and it's still going to be on the video, so that's helpful. But if y'all need to go to class, go ahead. I'm just going to go ahead and finish this out so I don't have to redo it next time. So what I've got is x of 0. If I look back, remember x of t is supposed to be a cosine omega t plus phi. So that's going to be x of t is equal to a cosine. Our omega turned out to be 11.83. So I'll say square bracket 11.83. That's an extra digit. That's fine. And that's in radians per second times t plus phi. So that's what my x of t is, but I'm not finished yet. I still got to figure out phi and a. Well, if I take condition 1, then that says that 0.0900 meters is equal to a times the cosine of In this case, it's just phi, because notice when I put in t equals 0, this whole part disappears. So I'm going to call this 1 prime. And now I'm going to take 2. Since this is this, I know that dx over dt, which is v of t, is obviously going to be negative omega a. Well, I'll say negative 11.83 radians per second times a times the sine of 11.83 t plus phi. I wrote it a lot smaller without units just so we could fit it in. Okay. So 2 prime is going to be me plugging the 0 in. So I'm going to say 0.00 meters per second is equal to negative 11.83 radians per second times a times sine of, and now evaluate at 0, that 11.83 disappears. I just get phi. Okay. That means I can solve for a sine theta, or excuse me, a sine phi, and I can solve for a cosine phi, and I can divide the two by one another. This is a really good technique to take two initial conditions when one's velocity and the other one's position, because one will be sine and one will be cosine. So obviously when you do that, the a's cancel out, and then sine over cosine, everybody knows what that is, right? Cheers times the shine, everybody. Okay, so that's tangent phi. Now notice a sine phi is just this. So I do 0 divided by this chunk. So that's just 0. And then a cosine phi is 0.09 meters. So that means phi is equal to 0. But we should have expected that. It's 0 degrees, or more specifically, 0 radians. Okay, but we should have expected that, right? I told you we don't always start looking at the mass on the spring when it's fully stretched. Well, this is the very definition of us looking at the mass on the spring when it was fully stretched, right? So I stretched it out to 9 and then let it go. If I would give it a push outward or give it a push inward, then that wouldn't be its max stretch, because it had some velocity before it ran into 0, or it would have some velocity at 9, so it would actually go higher than 9 on the other side. So we expected that phase angle to be 0, or we should have. Now that I have that, I can plug that back into equation 1 prime. So plug phi into 1 prime, and that gives us 0.0900 meters is equal to a times the cosine of 0. Implies a is equal to 0.0900 meters. And we're like, duh, of course that's what a is. Just like I said, we started it by pulling it out to its max height. So we now can say x of t is equal to 0.0900 meters times cosine of 11.83 radians per second times t. And of course, there's no phi in it, so I can just leave that off. And then v of t is going to be 11.83 times a times -1. So 11.83. So when I multiply the omega times 0.09, I get 1.065. So I'm going to write this as negative 1.06. And I'm going to go ahead and carry 2 sig figs, because this one's a little ambiguous, 4.8. So I'm carrying 2 extra sig figs. That's meters per second now, because it was radians per second for the omega and meters for the a. And that's times the sine of 11.83 bar radians per second times t. And then finally we get a of t is equal to negative, now I multiply this by 0.9 again, or 0.09 again, so I'll say times 0.09 or excuse me, times 11.83, excuse me. Ooh. So I get 12.6. So this is 12.6 meters per second times the cosine of 11.83 radians per second times t. So there's all our functions. There's our x of t, v of t, and a of t. And in fact, I'm going to go ahead and graph them again. Like I said, guys, your time's up. Y'all are free to go. I just want to put these graphs on this so it'll make some sense to you. But it's kind of cool. You can see now exactly what the graphs look like, because I can make one long vertical line to represent t equals 0. This first one's going to be x in meters. And maybe I'll draw it like this. And I'll say this is 0. The period, which we found was 0.53, if I remember correctly. The period was, yeah, 0.531. So that's the period right along this little red line. So that comes in super handy. I can now say this again is the time in seconds. This is the time in seconds. But this time, the graph right here is going to be V in meters per second. And then I can do it again over here. Again, marking that point off as the period 0.531. And t in seconds and 0.531. So you see the first one is just a cosine, and the cosine is going to look like this. Okay, so this should be the half point. This should be the quarter point. This should be the 1/4 point as well. So, and that should be the time. So now we can do that. This one's going to be a negative sign. So it's going to start off from, say, here. Since it's negative sign, it'll go down, reach 0, reach the maximum, and reach that. And of course, this quantity was 0.09, whereas this quantity is 1.064. And this quantity, which is A in meters per second, the peak of it is going to be 12.60. But that's actually going to be a negative cosine. So in this case, we're going to go from here to here to here, back to here, back to there. So the reason for drawing all this is so you'd see that, in fact, the velocity is 0 when the displacement is a maximum. And then the velocity is a maximum, in this case, in the negative direction when the displacement is 0. And then the acceleration, of course, is a maximum when the displacement is a maximum, but the velocity is 0. So that's mainly why I wanted to make sure I did that. So time's definitely up, but this is more than enough for us to get started. We've basically covered up through 14.2. Next time I'll probably finish chapter 14. If not, it'll take 2 more days. But you guys have a good one. Thanks for coming. And I will see those of you who have lab. The lab's already there if you want to look at it. If you want to watch any videos or anything like that, or read it or whatever, I will be there and see you at lab. Have a good one. Those of you stuck around, thanks. Gavin, do you have a question, bud?
No, I was around or following along rather.
Okay. Yeah, remember, I'm teaching you how we solve this differential equation, but the solution is not part of what you got to do. I mean, it's good for you to know it, but I wanted to make sure it's not a dogma thing. It's definitely something where I showed you the proofs in the pudding, right? So all you got to remember is those results that I boxed off, and you'll be golden. We're going to do next time, we'll do a pendulum, and we'll actually consider energy methods with regards to this. That's pretty straightforward. Then we'll do a pendulum, and then we'll do the harmonic oscillator, the mass on a spring with air resistance. proportional to V. And then finally, we'll do a forced harmonic oscillator, which again, we're just going to give you the solutions. I'm going to work it through. So you'll know that they are the solutions, but you're just going to record the solutions and use them like I just did these. Any
Gotcha.
questions?
All right, thank you.
All right, see you, Gavin.